Good morning, all of you. Let me just go back and complete something that were unfinished on the last occasion. So we are going to talk about different representations in quantum mechanics. They are called as Schrodinger representation, Heisenberg representation, and interaction representation. And then we'll talk about solution of Schrodinger equation in simple 1D potential. They would involve particle in a box, step barrier or a barrier, or rather a well, potential well, so to say, and then a bound state problem. Okay. So these are the plans for today, and let me start with this Schrodinger representation. And what we mean by that is that the one is that the wave function is time dependent, and the operators are time independent. So, all the operators are time independent, and we obtain the time dependence of the wave functions by solving this equation, which is the Schrodinger equation, which is what we have seen. And of course, they also, the wave functions also depend on the position coordinate. Right now we are just talking about the time dependence, and this gives you the solution that psi of t is equal to exponential minus I e t over h cross psi of 0. And so this is that factor that we have talked about, or there is a time evolution operator. Now, if you write it as an operator, then you have to write it as exponential minus I h t over h cross, but since we are talking about, so E is the eigenvalue of h. So that is how this E appears, and these are called stationary states because the mod psi square is independent of time. And in the other representation, that is the Heisenberg representation, we have just the reverse. We have the wave functions that they do not depend upon time, and the operators are time dependent. Okay. And the time dependence of the operators, they are written in this particular fashion. It is I h t over h cross O at 0. O is any operator, any arbitrary operator. It is exponential minus I h t by h cross, and so on. Now, this h is of course at this moment is really the h 0. So, you can write it as h 0 as well. Which means that there is a non-interacting Hamiltonian, there is no interaction involved here, which we are going to take into account just in the next slide, okay, where we talk about the interaction representation. So, these operators, they obey an equation of motion which is given by d o dt, that is the commutation of O and H. Okay. This is a function of t, of course. So, the time evolution of the operator, or the equation of motion for the operator, is the commutation of O with H. So, this is called the EOM, or the equation of motion. Now, in case an operator is not, it does not depend upon time, or say for example, some operator that commutes with Hamiltonian for all t, then of course, O is the constant of motion. Okay. So, let us talk about the interaction representation. which is more involved, and this is really for the interacting system, and in this case both the wave function is time dependent and operators are time dependent as well. Okay, so both are time dependent, and the time dependency are given as the psi of t is equal to exponential I h naught t by h cross, exponential minus I h t by h cross, psi of 0, and of course, it is true that the h 0 and h they do not commute, which means that this h is actually comprising of a non-interacting part, which is what we have taken in the earlier case. Say this case we can write it as h 0, okay, and these E corresponds to the E 0, that is the non-interacting energies, and then we have done this the same thing for for this Heisenberg representation. But in this particular case where both psi and O are time dependent, the wave function is the transforms as, or rather it is it can be written as exponential I h naught t by h cross, exponential minus I h t by h cross, and operating or on psi 0 multiplied by psi 0. Remember, you can't combine these two exponentials, because when you try to combine the exponentials, it automatically means that the two operators that are in the exponent, they commute, and in this case they do not commute. So, you have to leave it like this, and because if it does, if h 0 and h they commute, then of course there is no problem. I mean, then interacting systems will have no special status, or rather they do not have to be dealt with anything different than the non-interacting systems, but we know that it happens. Just to give you a clue, exponential a into exponential b is not equal to exponential a plus b, and is equal to exponential a plus b when a and b commute. Okay. So, that is what it is. So, if we what we can do is that we can look for the time or rather the this expectation values of operators, and these let us take an expectation values of an operator O, and in the Schrodinger representation. So, let me write it as SCH representation, and this is equal to, say because we are trying to calculate this expectation value. So, this is O at 0 and psi 2 at t. Now, if you look at the transformation of these wave functions, they are exponential. So, let me write it as exponential minus I h naught t by h cross psi of 0. That gives a form that it has been operated upon by an operator. So, this is equal to psi 1 0 exponential I h naught t by h cross O of 0 exponential minus I h naught t by h cross, and then you have a psi 2 of 0, and this is nothing but O of t. Okay. And you would write the expectation value of an operator O of t between the eigenstates or between the wave functions as this, which is the same as the Heisenberg representation. Okay. So, the expectation values which are really related to the observables, they have to preserve their form, and let us show that as well for the interaction representation. And so, we now have a psi 1 t O of t psi 2 t. Just to remind you that O of t is that's an arbitrary operator which could be anything, say for example Hamiltonian or angular momentum, linear momentum, etc. So, we have a psi 1 0, then we have an exponential of I h t by h cross. Remember, when you take the conjugate or this bra, then you need to change the ordering of the operators, and so that's what we did here, and exponential minus I h naught t by h cross. You can drop the h cross because it has to be carried around, so you can put h cross equal to 1. And then, so this part is nothing but the psi of psi 1 of t, okay. And then we'll write down this exponential I h naught t by h cross, then O of okay, let's this means O of 0, then exponential minus I h naught t by h cross. Then now this is nothing but O of t. So, and now we are going to write exponential I h naught t by h cross, exponential minus I h t by h cross, and finally we have a psi 1 at 0. Okay. So, this not psi 1, sorry, psi 2, psi 2. So, this is psi 2 of t. Okay. So, that is the expectation value in the interaction representation. So, these two, let me use a color here, these two are going to give me 1, and these two will together will give me 1, and that will tell you that this has the form which is psi 1 of 0, and then you have a exponential I h t over h cross and O, and then exponential minus I h t over h cross, and then you have a psi 2 of 0. So, this is the so it preserves the form of the expectation value, and if you you can now sort of write down the equation for or rather the equation of motion or the Schrodinger equation in this particular case with this definition, or rather in the interaction representation, which is exponential I h t h naught t by h cross exponential minus I h t by h cross. So, remember that not only you can combine the exponentials, you can't change the order as well, because this exponential is nothing but a series of power series of this h naught and h, that is full h, where h equal to h naught plus h prime. Sorry, I forgot to write this. So, h equal to h naught plus h prime, and that is what you should sort of you can't change the order of this. So, you have a ddt of psi of t, and it is e exponential I h naught t by h cross with the h naught minus h. There are two terms, because you have two terms, two exponential terms, and you have a minus I h t by h cross and a psi of 0. So, what you can do is that this h 0 minus h is nothing but, because h is equal to h 0 plus h prime. So, h 0 minus h is minus h prime, and that is equal to minus exponential I h naught t by h cross h prime exponential minus I h naught t by h cross psi of 0. And what you can do is that you can introduce this the outer product or this identity operator here, which is minus I exponential I h naught t by h cross h prime exponential minus I h naught t by h cross. Now, I am going to use this exponential I minus I h naught t by h cross exponential I h naught t by h cross, and then exponential minus I h t. Sorry, I wrote it twice. This is not required. So, minus, and then there is a plus, and then there is a minus I h naught t by h cross and so on, and then of course, a psi of 0. So, what I did is that I have not here, rather I have introduced the identity here, which is through this. Okay. So, this is equal to 1. So, I have just introduced a 1 there, and this tells you that the equation of motion for the wave function in the interaction representation is minus I h prime t psi of t. Okay. So, it is interesting to note that the time evolution of the operator is not given by either h naught, which is the non-interacting Hamiltonian, or h, which is the full Hamiltonian. In fact, it is given by this interaction term, and that justifies the name interaction representation. Okay. So, what we have learned is that there are different representations, and these representations are important, and they sort of tell you that if you really resort to calculation of the expectation values, then the expectation values will be independent of the representation, because they would simply be related to the experimental observables. Okay. All right, let's go on to the general solution of the Schrodinger equation. So, this is Schrodinger equation that you see, minus h square by 2m. Now, why it is written as u? It is for a reason that we have this psi of x t, and which can be written as say u of x and some f of t. So, right now we are dealing with the the time independent Schrodinger equation, and that is why the space part is written as u, but nevertheless, if you see in some text that they have written continued with psi of x, it really does not matter. I mean, they mean the same thing. It's u is a function of x, and it has either the form of a wave or a dying solution, which is what we are going to see. Okay. So, this is the form for this wave function, and rather the Schrodinger equation, and where V0 is the potential energy, which is a constant potential energy. That is, the potential energy is not dependent on the distance, and it has certain value, and the wave function is going to be continuous across that potential discontinuity, and it is always going to be continuous even if the discontinuity is infinite. That is, even if you have a delta function discontinuity, you still have the wave function to be continuous, but what is not going to be continuous is the derivative of the wave function for an infinite discontinuity. So, if you have a delta function, then the du dx is not going to be continuous, but nevertheless it is going to be discontinuous by a known amount. So, which is fine, which is something that we are going to see later. And so, this is the equation for a constant potential V naught, and E is the total energy. You can write this system or rather this equation as a second order linear differential equation, where the double derivative with respect to space is equal to some minus of some constant which we call as k square. We do not call it a k, we call it a k square, because the equation, the simple harmonic equation, has this form that d square y dx square is equal to some minus omega square x. So, that this omega is the angular frequency, and one can find out time period etc. From this, or the frequency of oscillations and so on. So, it is usually written as k square, where k is 2m e minus v0 divided by h cross square, square root of that. And for E greater than V0, that is when you have the energy of the particle to be larger than the barrier height. Suppose that there is a discontinuity like this, and so this is of magnitude V naught, and the energy of the particle is larger than V naught, then the wave that is going to be propagating is written as A exponential I kx and B exponential minus I kx, with k equal to 2m e minus v0 by h cross square square root. K is positive and real, and It's going to be a traveling wave here with k equal to root over 2me by h cross square, and it's going to be again a traveling wave here. Well, let me draw it inside, but it will be a traveling wave with a different k, where the k is reduced by 2m. I mean, this E will be reduced by E minus V0 inside that. So it will start, propagating inside. I mean, I didn't mean to say that it's inside, but it's the wave, the particle will propagate as wave even in the region. So let's say the discontinuity is at x equal to 0. So x less than 0, it's a wave with a wave vector. This is called as a wave vector. Wave vector k, and it's going to be propagating in the x greater than 0 region. So, this is x less than 0 and this is x greater than 0 with another k, which is this E is reduced by E minus V 0. Now, an alternative solution can also be written as A sin kx plus B cos kx. Now, this is important to note that whenever you have a finite region of space that you have to consider, which means that if there is a sort of discontinuity of this kind, where this is really a finite region between some minus a to plus a, or from 0 to a or 0 to L, then we do not use the exponential solutions, because the exponentials are going to oscillate even at infinity. Now, there is no infinity inside the box. So, you can of course use solutions which are exponential solutions which are on the left of the step, and I mean this kind of barrier, and on the right of the barrier, but inside one should use a sine or cosine, or if E is less than 0, then one uses a sine hyperbolic and a cosine hyperbolic. So, these are equivalent solutions as the exponential, the oscillatory solutions. These are called oscillatory solutions, and these are also oscillatory, but oscillatory in some confined region of space, because here in this the argument of sine or cos, you cannot talk about that to be equal to infinity and so on. Okay. Now, when E becomes less than V 0, okay, let me complete one thing before I go on to E less than V 0. Even at E greater than V 0, you see that the particle will recognize that there is a barrier that is below its path of propagation, even if its energy is larger than V naught. Okay. So, as for a classical particle, it will not even recognize that there is a small the barrier which lies below its energy, but in this quantum mechanical sense, the wave vector recognizes that there is a E and there is a E minus V 0 in the two regions that you see here. Okay. Coming to the E less than V 0, k becomes imaginary. Okay. And what we can do is that we can still use this notation, where this is called as a kappa, and this kappa is equal to root over 2m V naught minus E. So, if you look at it, kappa is like I, k and so on. So, we will still use kappa to be real and positive, but the solutions are no longer waves, they are exponentially growing solutions and exponentially dying solutions. And in some region of space, maybe one of them is prohibited due to the symmetry of the problem, or due to the boundaries that are set by the problem. But nevertheless, these are important solutions of the equations, because these solutions are needed because we need to impose the boundary conditions, and the boundary conditions are psi will be continuous, or u is continuous, u or psi, they mean the same thing, and d psi dx is continuous. And as I said, that this is only true for finite discontinuity, that is V 0 having a finite value. If it is an infinite value, then of course the second condition is not satisfied, that is d psi dx is not continuous, but it is discontinuous by a known amount. So, we do not really lose much information. We will show that in a while. If not today, then next class. Okay. So, the simplest problem that you do is that the particle in a box. Okay. And this problem is quite well studied, and one talks about these nanostructures and quantum structures, quantum confinement, and one really talks about this kind of picture where there is a potential well between 0 and L. L is some length, okay, and the potential is 0 inside the well, and the potential has got infinite barrier height. So, the particle cannot escape, and the particle cannot escape is imposed by V equal to infinity. And this V equal to infinity, if you look at the second term in the Schrodinger equation, that is this term, if your V is infinity, then the u has to be equal to 0, which means the wave function has to be 0, which means the particle is not allowed to escape from this region which is there in between the two barriers, the two boundaries of this barrier that exists at x equal to 0 and x equal to L, and this is that x there. Okay. So, we can write either, as I said, we can write either u or psi. Let us just write psi because we have written u, and we are going to continue writing u later on. So, now we are going to solve this equation, d square psi dx square now plus v psi, this is equal to E psi. Now, this term is equal to 0 because V equal to 0 inside the well. Outside, there is no question of solving the system because the particle is not there. Okay, by solving the equation, there is no particle there. So, you can write down this second order differential equation equal to minus 2 me by h cross square psi, and the solution is psi is equal to a sine kx plus a b cosine kx, following the advice or the suggestion that has been given earlier, that because it is a finite region in space, one can use the sine and cosine solutions, even though mathematically both are valid solutions. That is a superposition of sine is a solution, cosine is a solution, and because it is a second order linear differential equation, we can linearly superpose these two solutions to bring out a new solution, which is a sine kx plus b cos kx, and that is the general solution for the problem. But now you see there is a problem that the psi has to be 0 at x equal to 0, and psi also has to be equal to 0 at L. Okay. So, at x equal to L, the psi has to be 0, at x equal to 0, the psi has to be 0. Now, the first condition sort of prohibits the cosine solution to exist, because the cosine solution will not be equal to 0 at x equal to 0. In fact, it becomes just a constant b, okay, and which is what we do not want. So, we only keep the sine solution because the sine goes to 0 at x equal to 0, and so my first condition, we really do not need the d psi dx condition, because we have these infinite discontinuities there, but these two boundary conditions here, they are good enough for us to have a complete solution for the problem. Okay. So, this is the solution for this, and I will use now the second condition, which is psi of L, which I will write a sine k L, and that is equal to 0, means that is equal to sine n pi, okay, for any value of n equal to 1, 2, 3. Do not take 0, because 0 would mean that the particle is not there. Then of course, there is no point in talking about the solution. So, this say A, and so k becomes equal to n pi over L. Okay. And what else can be found out, right? We still do not know what is A, and that can be found out from the normalization condition, and the normalization condition is is in principle minus infinity to plus infinity psi mod square dx is equal to 1. But however, these two limits do not make sense, because everywhere the wave function is equal to 0, and if it is non-zero, it is only in this region 0 to L. So, we will write it as 0 to L psi square dx. And if you use this as a square, which is in general a complex constant, not in this case, but in general a complex constant, it is equal to a sine square n pi x by L dx from 0 to L, which is equal to 1. I leave this this integral to be done by you. You can just multiply and divide by a factor of 2, and then use it as a cosine 2 n pi x by L, and then perform this integral. This integral is going to give a equal to root over 2 by L. And then of course, what you get is that the wave function, then the full solution of the wave function is root over 2 by L sine of n pi x by L with n equal to 1, 2, 3 and so on, all these numbers, integers. And what is E in this case? What do the particles, what energies do the particle have? The energies are given by h cross square k square over 2m. That's only the kinetic energy, there is no potential energy there. So, this is equal to h cross square n square pi square by 2 m l square, again n equal to 1, 2, 3 and so on. Okay. Now, you see that the energy levels are not equidistant, they in fact grows as n grows as a square of that. So, in fact, there is another thing that you need to notice here is that the 1 over L square sits in the denominator, and because of this term, if you decrease L, the spacing between the energy levels will go up, and that is an important concept that we use in quantum confinement. So, if you confine a particle more and more, the energy levels that will become more and more discernible, they are identifiable, and because they are the distance between the successive energy levels become that increase. Okay. All right. You can also see the correspondence principle from here, and you can so what is the correspondence principle? We'll use this. So, let's call this as E n and call this as psi n, and so psi n's are called as the eigenfunctions of the system. And E n are called the energy eigenvalues, eigenenergies or energy eigenvalues, anything you can call it by. And each of these psi n's they form a complete set of states because of these psi n star psi m dx, that's equal to delta nm. Okay. Which means that this really can be written as in your Bryan-Kett notation as this delta nm. So, if n is not equal to m, this overlap or the inner product is 0. If n is equal to m, then it is equal to 1, which is what we have used for our normalization. Okay. So, that is why they are called as the orthonormal. They are both orthogonal and normalized. So, that is called as a orthonormal set. And now, you notice that n can be any of the integers, that is n equal to 1, 2, 3, 4, 5, anything is allowed, I mean very large numbers and so on. And so, we were talking about the cat being dead or the cat being alive, which really gave us only two states, or the coin being tossed gives you head or tail. There are two solutions or rather two situations that can arise. But here for each value of n with n to be unbounded, any of these are actually the eigenstates of the system. Okay, and that's why this entire linear vector space that we are dealing with is called as a Hilbert space. So, in that connection we want to understand that what is E n plus 1 minus E n divided by E n, say for example. So, this is like n plus 1 whole square minus n square divided by n square, and this is like n square plus 2n plus 1 minus n square divided by n square, and the n square will cancel, and if n is large, then of course we can neglect 1 in front of 2n. So, this really goes as 2 over n and will go to 0. This energy spacing will go to 0 as n tends to infinity. Okay, and that is the correspondence principle, Bohr's correspondence principle that we have learnt earlier. Okay. Let me add a little bit of trick to this problem, and before that let me show you this different energy eigen modes or eigen values, rather eigen functions. So, n equal to 1, which is called as a ground state, that is the lowest energy state, which has got an energy which is equal to pi square h cross square by 2 m l square. This has only nodes at the two edges at 0 and at x equal to L. Then the red one, which has got energy which is 4 pi square h cross square by 2 m L square, because n equal to 2. So, it goes as n square is 4, and then it has a 9 pi square h cross square by 2 m L square. Now, you see the red one, that is n equal to 2, has 2 nodes at the two edges. Nodes means the wave function goes to 0. The wave function has to go to 0 at the edges, because the particle cannot escape and the wave function should be continuous everywhere. Now, there is also a node at L equal to 2. Okay. So, that is at the midpoint, and then you have for n equal to 3, there are apart from the 2 nodes at the edges, there are 2 more nodes at these points and these points and so on. So, maybe L by 4 and 3L by 4, n equal to 4 has more nodes here, here. So, as you go to larger and larger n, the wave function starts oscillating rapidly. Okay. And this, so I have just plotted 4 of that, but you can go ahead and plot more. And one more thing that we have said is that the energy levels are not equispaced, that is they are, so this is small and then this is larger than that, this is larger than that, and it will be progressively larger because it varies as the square of the quantum number. Okay. And then going on to the probability density of these things for each of these states, we are showing 3 of them. You see that the probability density, which is psi square, is for the lowest state, it is the probability density peaks at the middle of the well. So, the particle is most likely to be found at the middle of the well, and as you go to n equal to 2, it is equally likely to be in the left half, the middle of the left half and middle of the right half. And then as you go to n equal to 3 and so on. So, you go to larger and larger and these oscillations will increase, because you are taking psi square, or rather this is actually psi mod square here, because we are talking about real eigenfunctions. We did not put this psi square, but in principle one should put a psi square, and because it is a psi square, it does not go to negative, but it goes to it always takes positive values and wildly oscillates as you go to larger and larger n. Okay. And so, which means at large n, it is likely to be found anywhere between 0 to L. Okay. So, that is what it means. All right. So, let me do one more problem. So, it says that the particle is likely to be found anywhere for large n, and that is the one that we have talked about in connection to the correspondence principle. Okay. So, what will happen for the well to be symmetric, which means that the well is not between 0 to L, but it is between L by 2 to minus L by 2 to plus L by 2. So, this is 0. Okay. So, this is the x axis, and the same problem remains. These are infinitely large walls, the particles cannot escape, and you just think that maybe the well is simply shifted to the left by a distance L by 2. How would the particle react to it, or how would it know, or what would be the change in wave function? There shouldn't be any change in wave function. But unfortunately, there is a big change in the wave function. In fact, what we can show is that your psi of x was nothing but a sine k x earlier. Okay. And now, what you do in this particular case is that you write it as a sine k x minus L by 2, because all the x coordinates have been shifted towards by this x minus L by 2. So, what we can do is that we can expand this sign of c minus d kind of thing, and we can get it a sine k x cos k L by 2 and minus a cos k x sine k L by 2. Okay. That is what you get when you use this expansion of the signs. So, you have k equal to n pi over L, which is the same quantization that we use. We can use a k of n, and then the cos of k L by 2. Let me just remove this k L by 2 to be equal to cos n pi over 2, which is equal to 0 for n odd. For example, 1, 3, 5 and all that. And similarly for the other one, so this is for the first term. For the second term also k L by 2, which is sin n pi by 2. Now, this is also true that this is equal to plus minus 1 for n to be equal to even, okay, which means that 2, 4, 6 and so on. Okay. Now, similarly for the sine, one still has k L by 2 is equal to 0 for so sin n pi by 2 for n equal to 0 for n equal to even, and this is equal to plus minus 1 for n equal to odd. Okay. So, that tells you that the first term would be not an applicable solution for n equal to odd, because the associated coefficient is 0, while the second term, which was earlier not the solution, which is a cos k x, is actually going to give you the solution for n equal to odd. So, the solution, so psi of n x is equal to again the same normalization in sin n pi x by L for n even, and psi n x is equal to root over 2 by L cos n pi x over L for n to be equal to odd. Okay. So, you see the change in the stand of this, that instead of simply a sine and cosine solution, I mean simply a sine solution which was there for the well that we have seen earlier, this is not only a sine solution, but also a cosine solution depending on whether n is even or n is odd. So, this is the for the symmetric well we have both the solutions allowed, and so the sine solutions will be n equal to even for even values of n, and the cosine solutions will be n equal to odd, and put together they would define the entire vector space for the problem. Okay. So, what is important here to note is that there is another additional symmetry that is present in the system, because if you put x to minus x, or rather if you draw a line at the this dotted line that you see at x equal to 0. So, there is a symmetry, a left right symmetry, and this is called as a parity. So, this because of this parity symmetry, the wave function has a left vector, or it has a left property and a right property. So, the entire vector space actually fragments into left and right, and this is a property, special property of systems with a parity or the inversion symmetry. Okay, because any x corresponding to a x here, there is x minus x here. So, for any x there is a minus x, and this symmetry is called as an inversion symmetry. If a system has an inversion symmetry, then the eigenvalues will be either even or odd, and they would put together would define the entire space, entire Hilbert space. Okay. So, what we are going to say is that not only we got these solutions, but how do we make use of these solutions? Can we make something useful along with this what we have already discussed? And it turns out that yes, it is of a lot of use. Let us sort of derive, or rather verify, not is confirm the Heisenberg's uncertainty principle. How do we do that? I will not do that. I will tell you how to do it so that you can do it. And what you can do is that you can calculate x, and x is nothing but x and then a psi square x dx from minus infinity to plus infinity, but here you know that the only relevant region of space is 0 to L, and this is nothing but equal to L by 2. You can also calculate x square. So, with I go back to the old problem, which is 0 to L, the solutions are sin n pi x by L. So, 0 to L again, x square psi of x mod square, and you can again calculate this. This is equal to some L square and 2 pi square n square minus 3 divided by 6 n square pi square, and so on and so forth. Okay. And then you can calculate delta x square, which is equal to x square average minus x average square, and you can also calculate p, but for calculating p you need to be a little more careful. You have to use this psi star x minus I h cross d dx of psi x. So, do not take just psi star and this, and you can also calculate p square, which is equal to psi star x, and so minus h cross square d2 dx2 and psi of x and dx. And you can calculate a delta p square as well by taking so delta p square, you do not have to take a square root, because from there you calculate delta x. So, let us talk about just delta p, which is the square root of p square expectation minus p expectation square, and now you see that whether delta x delta p gives you the value that you want, it should be of the order of h cross. So, this is the uncertainty principle that you can test. Okay. And let us understand that what would be this stationary states in. So, these, if you want to evolve these wave functions in time, what you would do is that psi x t is equal to root over 2 by L sine of n pi x by L exponential minus I E n t by h cross, okay, where E n is given by n square pi square h cross square by 2 m L square. Just to remind you that even for the symmetric problem, even though we have sine solutions and cosine solutions, both are acceptable ones, energy is still given by this n square pi square h cross square by 2 m L square. Okay. And so, this psi x t, that is the probability density, is constant in time. Constant in time, it's not, I am not saying that it's constant in space, because we have already shown these variations within the well. Okay. So, constant in time for all time, okay, because the time goes away. Now, let us look at the linear superposition and form a wave packet, which is what we have learned as well. And wave packet. Okay, so let us say we have wave packet comprising of the linear superposition of this psi 1 x t plus a psi 2 x t. So, the particle is in a superposed state of the ground state and the first excited state. It is like, say that we are removing all the other possible eigenstates, and we have prepared the system in such a way that it can be either in this ground state or in the first excited state, just like head or tail problem. Now, this is it's a 1 by root 2 and so on. So, it is so there is a root 2 by L. So, the root 2 cancels and there is a L here, and then we have a sine pi x by L, that is the ground state, exponential minus I, say for example E 1 t by h cross, and plus sine 2 pi x over L exponential minus E 2 t by h cross. Okay. So, that is the wave function. Now, this is between, of course, 0 to x less than L, it's otherwise it is equal to 0, that is very easy to see. Now, one important thing is that how do we interpret this, or rather what is the probability density, is it still a stationary state and so on. No, it is not a state that's whose probability density is independent of time, because it does not have definite energy. It has, if you make a measurement, it will collapse onto one of the states, that is either in the ground state or the first excited state, but it still has the energy to be with certain probability you will get if you make a measurement before you actually make it. You would get the ground state energy with certain probability and the first excited state energy with certain probability, which were respectively given by pi square h cross square by 2 m L square and 4 pi square h cross square by 2 m L square. So, this probability density is going to be oscillating with time, and if you calculate this p x t, which is nothing but equal to mod of psi x t square, and this will give us equal to 1 over L, and then you have a sine square pi x by L plus sine square 4 pi, there is a sine 2 pi, sine square 2 pi x, not 4 pi, 2 pi x by L. And then we have a 2 sine pi x over L, sine 2 pi x over L, and then there is a cosine of a delta omega t. Now, that is the time part which is coming from the interference, where delta omega is nothing but E2 minus E1 divided by H cross. Okay. That is the time part with which it will oscillate, and I have made a video where the L is varied from 0 to 1, 1 is some unit of length, and then T has been taken in unit of omega, such that this it cancels out, and you see that as time increases, it changes from being in the left part to the right part, then it comes and gets reflected on the left boundary of the well, and then it goes to the right boundary, and so on and so forth. Okay. So, it sort of gets reflected from here and go to the. So, this is the initial time you have it in the left side or left half of the well. As time progresses, it sort of evenly distributed, or rather equally distributes both sides of the well. Then later at larger times it goes to the right half, gets reflected from the boundary, again reappears at the left edge, and so on. So, this is the animation for the probability density at different times. Okay. All right. Let us now do a number of problems, and I'll sort of keep this thing a little quick now, because now you are familiar with how to handle this and what are the boundary conditions. All what you have to do is write down the Schrodinger equation and match the wave function, or match the solutions at the boundary. First you have to get the wave functions. So, what we did is that here there is a potential step. The step is that of height V naught, okay, and a particle is coming from the left whose energy E, shown by the green dashed line, is greater than V naught, okay. And we want to calculate what are these R and T, which are called as the reflection and transmission amplitude. R is reflection amplitude, and T is transmission amplitude. Okay. So, there are a few comments that will help you to solve this problem. There are two cases. One is E greater than V 0. We are showing at this moment by the green line E greater than V 0. That is shown here. E less than V 0, which should be more interesting. That is a particle which would appear with lesser energy and has energy lower than the barrier height. A classical particle can never jump over to the other side or get into the region which is classically forbidden. Say a high jumper would never be able to cross a barrier which is more than what he or she could jump. Okay. So, but here any particle such as an electron or photon and so on, they will go into the classically forbidden region, and go into means there will be sort of the wave function would be finite, but they won't correspond to any propagating wave. Maybe those are called as the evanescent wave, but the wave function would still exist, which means that there is a probability of the particle to be found in the classically disallowed region, or the one that is forbidden region will still be found. And we will have to match the boundary conditions at x equal to 0, and the reflection and the transmission amplitudes R and T will have to be calculated. And sometimes in questions you are not given this figure, but you are given it in writing that V of x equal to 0 for x less than 0, and V of x is equal to plus V 0 for x greater than 0. They mean the same thing. You will have to picturize this and draw your own schematic diagram. So, as we have said that we are first doing it at E greater than V 0. So, for x less than 0, we have this u of x which is the solution. We again go back to the notation u, but they mean the same thing if you write it as psi. it's exponential ikx, so which has a coefficient equal to 1, and in keeping with what we have said that because it's an infinite extent both in the left and in the right, we write exponential solutions. So there is a amplitude 1, part of it is reflected, so we call it r, and a part of it is transmitted, we call it t. So k is given by, so this amplitude is equal to 1, if you that's why it's not written there, and so this r is the reflection amplitude, k is equal to root over 2 me by h cross square here. For x, sorry, this has to be x greater than 0. So, x greater than 0, you have u prime, which is the solution in the classically, not classically forbidden here, because E is greater than V 0, it is in the right region, right of the discontinuity. You have 2 m E minus V 0 by h cross square, and the transmission amplitude and exponential I k prime x and so on. So that the current is conserved, the solution is written in this particular fashion. Okay. So, there is no reflected wave because there is in the second solution, that is x greater than 0, because you see that there is nothing to reflect it back. So, it is only a solution which is exponential I k prime x, even though there is mathematically it is possible to write exponential minus I k x. However, we see that that solution will not be acceptable solution, because there is nothing that is reflecting back the wave to move in the towards the barrier, okay, or towards the potential discontinuity. So, there is no reflected wave for the second one. And so, what we have to do is that we have to the boundary conditions have to be matched for x equal to 0 for the wave function, and x greater than 0. So, the boundary condition is for x equal to 0. So, it really does not make sense. So, we can just simply write x equal to 0. So, this is not acceptable. So, this boundary condition have to be matched. We have written down the solutions, put x equal to 0 and match the u and u prime, and that gives 1 plus r equal to t. So, if you put x equal to 0, the first term on this it becomes 1, this becomes r, and this becomes t. So, it is 1 plus r equal to t. Then the other boundary condition, which is the derivative of the wave function at x equal to 0, also is continuous, gives you take the derivative and then put x equal to 0. If you write them down and then put x equal to 0, and then you eliminate t and write it in terms of r, and now finally you solve for both r and t. They are k minus k prime, k plus k prime, and t is equal to 2k divided by k plus k prime, with all these k and k prime given in terms of E and V naught. And also, of course, m and h cross square, they have to be there along with the mass of the particle and Planck's constant. So, the wave functions in the two regions are now, because we have calculated r and t, can be written as exponential I k x, k minus k prime divided by k plus k prime, which is the amplitude, exponential minus k x for x less than 0, and for x greater than 0, it is 2k divided by k plus k prime, exponential I k prime, this is equal to 0. So, this transmission amplitudes and the reflection amplitudes can be squared up to get the probabilities for reflection. Sometimes you will see that in some books this r and t, capital R and T, are written as small r and small t, and the P reflection and P transmission are written with capital R and capital T, but nevertheless they mean the same thing. So, this reflection probability, or this is the reflection coefficient, at times it is called. So, reflection coefficient and transmission coefficients are given by these k minus k prime whole square divided by k plus k prime whole square, and 4k k prime k plus k prime whole square. You can simply see that they obey that 1 plus so this reflection plus transmission, if you add up, you would get it. So, there is so PR, let us call it, and a PT, that is the one that you see here. So, you have a k minus k prime square plus 4 k prime, and this is equal to k plus k prime square, and this is equal to k square minus 2 k prime plus k prime square plus 4 k prime divided by k plus k prime square. This is equal to 1, which means that the reflection coefficient or probabilities of reflection and probabilities of transmission add up to 1, which they should. Okay. The wave is not getting lost, it is not going anywhere. So, these two probabilities should become equal to 1. And I leave it to you to do E less than V 0. The hint is that for x greater than 0, which is in the, now you have the particles energy to be lesser than this barrier height. So, you will have this k prime to be actually a complex quantity, and you write it as kappa the way we have shown, and so on, and you get it as exponential minus kappa x, and where kappa is equal to I k prime, which is equal to 2 m v naught minus E by h cross. Okay. And you will see that the result is that the reflection, this coefficient or probability of reflection is equal to 1. So, the particle will be totally reflected back, although this region, which is classically forbidden, has a finite probability of the wave to exist, and this is actually given by this. So, there is no current associated with it because it is fully real. Remember, the current density is these h cross h cross by 2 mi psi star del psi minus psi del psi star, that is equal to 0 because there is no difference between the first term. So, the current is given as h cross by 2 mi and psi star del psi minus psi del psi star, that is equal to 0, and the reason it is 0 is that because psi is real here. So, it should not have the first term will cancel exactly with the second term. And what you see is that it is a travelling wave in the region that is, or it is called as a standing wave in the region which is left, and then it is an evanescent wave and falling off to a value which is called as a this value at which it falls to a value 1 over E inside is called as that exponential minus kappa x. So, kappa equal to 1 over x is called this skin depth, and in optics this would correspond to a denser medium to a rarer medium, which means that n1 is greater than n2 in terms of the refractive indices. Okay. All right. Continuing along that line, so we have these potential wells that are shown like this, and where you have exponential ikx, r exponential minus ikx, again t exponential ikx. Now, E is greater than V naught, which is easy thing to do. The results for these reflection amplitudes and transmission amplitudes are a bit complicated, but one can simply write down the solutions in the 3 regions. Now, you have a region 1 and a region 2 and a region 3, and you have these discontinuities at at 0 and a and so on. So, you have to match the boundary conditions at x equal to 0 and at x equal to a or for both the psi being continuous and d psi dx being continuous. So, if you square them up and add them, this will give you the total probability. There is something interesting happens if you look at it. If you look at the reflection coefficient which has a sign 2 k prime a in the numerator, and sign being a harmonic function, it will tell you that this reflection will go to 0 for certain values of this k prime, and k prime is a variable because k prime is related to energy. It is 2 m E minus V naught and so on and so forth. So, because it is related to energy, so k and k prime are the 2 wave vectors which are written here these wave vectors that you see on the screen. So this is so this sine 2ka that you see here is will make the reflection amplitude to go to 0, and you see that for those values when 2k prime a becomes n pi with k prime equal to this, you have a complete transmission because the reflection goes to 0, and these are the values and so on. Okay. And this is for a particular value of V naught and the width of the well, and it's plotted as a function of E in terms of 1 by length square, that's in angstrom, and this plot is adopted from an AMJFIS article in 2010 by Uma Maheshwari et al. The energy is still given by minus V 0 because it has a minus V 0 energy. You see that it's minus V 0. So, it is a potential well. Okay. So, this is V 0 and so on. So, it is minus V 0 n square pi square h cross square by 8 m a square and so on. And E less than V 0 are called as the bound states. I will sort of do it quickly. And so, we have these solutions. You can again write down these equations and do necessary simplification of that. So, psi of x is equal to it's a cosine k 1 x, and just to make it a little interesting, I put this these discontinuities at x equal to minus a and x equal to plus a, so that this even odd solutions they would arise. And so, it is a cos k 1 x for 0 less than x less than a, and this is equal to well, I mean I am writing it as k 1 and k 2 instead of k and k prime, but I will define what are k 1 and k 2. So, this is c exponential minus k 2 x. By hand it is a little difficult to write this kappa, or you may actually misunderstand it as k. So, that is why I am writing k 1 and k 2. So, this is for x greater than a, with these k 1 to be equal to 2 m by h cross square E plus V naught, okay, because V naught is negative here, a square root of that. And or you can also write it as this one as 2 m by h cross square V naught minus E, where this E is actually negative. So, I have taken a mod of E, and this is for within the well. So, that is like mod of x is less than a, which means that we are talking about inside the well. Okay, so these are the solutions, and so these are the even solutions, because now we have this even and odd solutions, and then so this odd solutions would look like psi of x is equal to b sine k 1 x. I mean, in the sense that what I meant to say by even and odd is that if x changes to minus x, cosine does not change its value. Cosine is a even function. So, it is in that sense that we talk about an even and odd, whereas sine changes. Of course, if you change x to minus x here in the second solution with the c exponential minus k 2 x, that will become plus k 2 x, which is not a physically acceptable solution. So, our even and odd notion is based on the harmonic solutions, which are either cosine or sine. These even solutions are truly valid for odd n, and odd solutions are in fact applicable to even n. So, but this even and odd is with respect to changing x to minus x, that is why we call odd and even. So, this is for 0 less than x less than a for the odd solutions in the same region, that is so this is your that is your x equal to 0, and so on, and so this is V 0, and energy is negative. So energy is negative, but it is greater than this V 0 minus V 0. It's greater than minus V 0. All right, and this is equal to some c exponential minus k 2 x for x greater than a. So these are the solutions. Now what we can do is that we can do a smart thing of combining the two, psi being continuous and d psi dx being continuous. So this two can be combined into a single condition, in which is say that 1 by psi d psi dx is equal to continuous. So instead of writing the two conditions, we can also use this 1 by psi d psi dx being continuous. That gives us two conditions. One is k tan k 1 a equal to k 2, and k 1 cot k 1 a is equal to minus k 2. So this corresponds to the even problem, or this corresponds to the odd problem. Okay. Now you see that there is a problem in solving these equations, because the k 1 and k 2, they correspond to energies which are there in both right side of the equation, and cannot be solved so easily, and these are called as a transcendental equations. So one way is to solve them numerically, which is what we are not going to do here, but what we can do is that we can plot these solutions, and these solutions can the intersection of the left hand side and the right hand side will give us the solutions that we are looking for. So a little bit of different language. Let me sort of give you that. If you say k 1 a is equal to y, then k 2 a whole square, this is equal to 2 m by h cross square v naught minus mod of e, and so this into a square. And let me actually create again a page so that it is easily understandable for you. So okay, so what we do is that you call k 1 a is equal to y. We have used different notations for plotting, but I'll tell you what these are. And now you have a k 2 a square is equal to 2 m by h cross square v naught minus e, and this multiplied by a square. So that tells us that k 2 a square is equal to 2 m by h cross square v naught a square. For a given problem, that's a constant, and minus 2 m mod e divided by h cross square a square, and this is nothing but, let's call this as lambda square minus k 1 square a square. So k 2 square a square equal to lambda square minus k 1 square a square, and call this as lambda square minus y square. So k 1 and k 2 are positive, and also we have a k 1 plus k 2 square, k 1 square plus k 2 square, and a square is equal to lambda square, because you can add both of them, and then where lambda is equal to nothing but this 2 m v naught a square divided by h cross square whole to the power half. Okay. And here let us sort of show So, these are the solutions of these xi, tan, xi, where we have probably the calculations done on the last step was not that necessary. So, this K1, so K2 is equal to K1 tan K1 A. Okay. So, your xi is equal to K2 and eta is equal to K1, and A could have been taken as 1. So, if you plot this xi and eta tan eta, then these lines that you see here, let me sort of redraw them, like these ones are the tan solutions. Okay. And these solutions that you see are these ones that are given by these k square, k1 square plus k2 square is equal to some lambda square, which is what we have derived here. I mean, the A has been taken equal to 1, but you can just add this, I mean, there is a square here. So, that is equal to lambda square, which is nothing but a circle. So, you see that you now plot the circle, which is say the blue line, and the tan hyperbolic. So, you see these solutions to emerge at say for example, these bright red point. These are the solutions where these are the bound states. So, this is the deepest bound state and this is the bound state for some other bound states and so on. So, we have shown two of them. The more the depth of the well is, you have these there will be more and more number of bound states there. And for the odd problem, which corresponds to this K1 cot K1A is equal to minus K2. Now, it is a cot solution which does not go to 0 at or does not start from eta equal to 0 or K1 equal to 0. In fact, it starts from pi by 2, and one can actually see that. So, there are these it starts from pi by 2 there. And if you have a circle which is nothing but this eta square plus xi square equal to z0 square, which in our language is nothing but a square k1 square plus k2 square equal to lambda square. So, if this circle has is like this, then there is no bound state. Okay. So, for having a bound state, an odd bound state, you need to have a certain depth of the potential. So, for any infinitesimal potential, you can only have a even bound state, but for having an odd bound state, you need to have a particular depth for the potential. And so, there is a solution that emerges here, which is we have shown it in color. So, there is a solution which is here, and we have just shown one solution, and this is the part of the circle of length, either you call it z0 or you call it lambda. So, z0 is nothing but this lambda. Okay. So, that is the solution that we have for these bound states, and there are these bound states that are formed, and you can be given a certain depth of the well, and you can calculate the number of bound states present from these conditions. That is how many times this circle crosses. If you are talking about an even bound state, then any infinitesimal depth of the well will give rise to a bound state. However, that is not true for the odd bound state. You need to have a critical depth to have at least one bound state. Okay. So, we stop here for now, and so this is what is written there, or no odd bound states below a critical depth of the well. So, we will stop here and start with some more problems in quantum mechanics involving perturbation theory and Stark effect and so on. So, we start with time independent perturbation theory, and then go over to this time dependent perturbation theory. Okay. Thank you.